Okay. Um, so, ladies and gentlemen, uh, I'm going to be going on a brief basis in this presentation through motivations for scalable software engineering for data science. This will be part one of it, and we're probably going to need to finish it next time because of time constraints. So this course focuses on software engineering for data science. Data science is a fairly recent term to describe a field that seeks to provide systems, methodologies, and procedures for securing insight from data. And as such, it spans the gamut from statistical and algorithmic analyses tools, what our colleague Jeff McDonald sometimes calls not only analytic but synthetic methods based on dynamic modeling, techniques like CCM I'd put into here for operating data at scale, but also data curation, provenance recording, a recording of where data results came from, like what data was used to produce this output data, what algorithms and what version of those algorithms were used to produce it. Data science also encompasses infrastructural issues. How do you build computer systems, larger computer systems, so that they can operate in a performant way to provide the insights we need to make more effective decisions informed by data. It further relates to aspects of the programming languages we might use to build that, and indeed the software engineering. Much of data science, and I would say most of data science currently, focuses on this area that's sometimes known as big data. Focuses on processing and making sense of very large volumes of data, which are a defining feature of our age, and in fact of the job market for many graduating from our program. So given that our group focuses on applications in health areas, I'd like to give you a sense of some aspects of big data in health, just so we have some clear points of reference. These would include search volumes, data from Twitter feeds, Facebook status updates, billions of which occur probably daily. Data from environmental sensors. Our buildings are increasingly robots around us. In modern buildings, the building measures temperature, humidity, pressure throughout the building, airflow. And that's used to control the ventilation, but it can also be used for decision-making insights, such as trying to find why is it that certain infections are spreading in a hospital. Data from lab tests, from imaging, for example, that takes place in a hospital could be considered aspects of big data. Point of sale records. Every time someone purchases something, makes a transaction, those are aspects of big data some companies are mining extensively. Administrative data. This is data from like billing by doctors and allied health professionals like chiropractors or physiotherapists or occupational therapists, etc. Our healthcare system maintains massive quantities of data on all these transactions related to health, prescriptions that are filled of great interest in understanding use of drugs and understanding things like the opioid epidemic. Questionnaire responses, such as we gather from Ethica via mobile data sources and shortly with Ethica the web. Sequence data from DNA or protein sequences, weblogs. People have done analyses on weblogs for Wikipedia, for example, for people searching out health terms on Wikipedia. people seeking to understand symptoms of flu over time from a given region might give you a clue as to what's going on in that region in terms of spread of flu. Audio, well, we know not just voice, but crying sounds, right? And coughing, and snoring, and sneezing, and laughing. All of these can be helpful for understanding health issues, mental health, more areas of immunological health, etc. Incoming, outgoing calls, consumer electronic devices, also on phones, such as we use so much with the Ethica system. So sensors such as the accelerometry, the GPS, the gyroscope, and Bluetooth for proximity to another person or to a dog, a service dog, and supply chain data. Now, this data comes in a variety of levels of detail and frequency of update. On the one hand, we have mobile data collection, such as we get with Ethica, where we might get, every minute thousands of accelerometry data points for much of the time points, or we might get GPS measurements every few minutes. Something like Twitter can give us a lot of data over time, but on a per person basis, it's a lot less frequent. Then we can get very aggregate things like search monitoring. All of this, though, is joined by certain features that I'd like to highlight. And I personally really dislike the big data label, particularly when it's used in the sense, so there's a certain segment of the technological community that uses big data to refer to data of such volumes and types that it requires new generations of technologies to process it. Okay? In other words, you can't just do traditional relational database, SQL. You have to go to NoSQL. You can't just use your traditional R or SAS. You have to go to something like Spark to do data analysis at scale. I don't find that very helpful because the boundary there evolves over time. What R can do has been changed a lot in recent years because of Shiny and its interface actually with Spark, for example. What I find more useful in the term big data is what are sometimes termed the 4 big V's of big data. And I don't know why this is so small, so I will make it large. I will make it big, okay? So the 4 V's are defined by, the fact that it's high volume. That's the big as in big data. There's lots of data there. But in my view, that's actually the least interesting of the 4 V's. Yeah, it's true, and it requires a lot of extra attention, technology-wise. But the other 3, in terms of insight, are often much more substantive. It's high velocity. What I mean by this is it's longitudinal. So for a given individual, for example, we'll get their tweets over time. Or we'll get accelerometer data and GPS location for them over time. And the velocity is referring to how quickly that comes in. It comes in very quickly compared to traditional data sources. In traditional health research, if you were doing fairly aggressive longitudinal sampling, you might call that person once a month. Here we might get every 5 minutes many data points for this person from their accelerometry. We may get several Facebook status updates in the course of a day. We may get a few tweets from them. So this is very high velocity data. It comes in very frequently. It's high variety data also, and this is of great importance. So from our phone alone, from Ethica, right? For a given study, we might get GPS, which includes lat, long, altitude, I think, and accuracy. But we also would get accelerometry. We get gyroscope, give you an indication, together accelerometry, are they sitting, standing, lying down? Are they walking? What sort of activity are they engaged in? We might get Bluetooth, their proximity to their service dog. We might get self-reporting by them about their mood that day. When was the last time, they had a cigarette? We may get data related to their physical activity context as deduced from accelerometry that gives us a great deal of understanding. We might get data related to their browsing behavior. For our work with DFCI, Dana-Farber and Harvard, we were doing work looking at people's browsing and what they're browsing to related to cigarettes and e-cigarettes. So there, we might get many aspects of their browsing in the course of a day, many URLs that they reach. So this is high velocity and high variety as well. It's many types of data for that same person in the same period of time. And that's really important because often you can use those to triangulate on what's going on. Another component is veracity. For a lot of areas of health, particularly health behavior and social behavior, things are either not reported accurately by people or very burdensome to collect, or both. Example is what people are eating, how much physical activity they're getting, how much sedentary behavior, to what degree they're really moving about in the day versus sitting in a chair versus lying down, etc. Aspects of their social context, who they saw for the day, where they're spending their time, what they browse to. Turns out that many of these things, health research has shown, and some of our own research has shown, people self-reporting them are very poor. Even like where you spent most of your time during the day. Our work here with university students suggests that what they report is often very different from where they actually spend their time as recorded by GPS and the location sensors on the phone. And it's not because they're leaving their phone at one place. Their memory is just not very good. And to some degree, it's related to their expectations of themselves. When we asked a student cohort some years ago about where they spent their time here for undergrads, they reported 3 primary areas: in the classroom, in the gym, and in the library. In other words, they study hard, they work out and invest in their health, and they're going to class. Oh, they also mentioned Place Real. Yeah, they spend quite a bit of time in Place Real. When we actually measured where they spent their time using their phone, we found it was a very different situation. They didn't spend that much time in the pack, very little in the library. They spent quite a bit at Place Real, hanging out with friends. And yeah, they spent some time in the classroom, although maybe not always as reliably as one would like. So they were poor. We also asked them to report in a previous study, the one that UN was involved in the very first time. We asked them to report who they spent time around, who they spent most time around that day. And actually, there are big gaps between what they reported and what the data suggested from detecting proximity of data. People have a hard time remembering and quantifying, how much time did I spend around this person or that person, particularly transient contexts, like who did they stand next to in Tim Hortons line? Who were they next to on the bus, on their way in, etc. Or who else was on the bus? And more to the point, when we asked that question about who they spent time with, after a week or two, they refused to answer it because they found it so burdensome to try to remember. So the point is, these things are hard for people to remember often and burdensome to collect. Even things like what people eat, you would think would be obvious, but just remembering what did you eat for lunch 3 days ago, it's hard. But with a lot of these types of data, we can get better understanding of these things. We can get a better understanding of where they are, who they're with, what they're eating through camera, right? We get them to take photos of their food. Or you look at what they purchased food-wise. They purchased a Frappuccino, and you have some understanding of their consumption habits. So we have this phenomenon of veracity. And sometimes the issue isn't that any one piece of data, like accelerometry, is super accurate, but rather you put a bunch together and you get a better picture. We did some really interesting work. William Vanderkamp in the lab was quite involved in it back in the day, using machine learning to try to classify, are people sitting, standing, lying down, walking, active, active, inactive, so sedentary, and if sedentary, what posture. Accelerometry by itself, not so good. Gyroscope by itself, not so good. Look at combinations of them, now you're talking. You can actually do quite good jobs. And once you start putting together several data points, like Chin Yang did for analyzing when people are smoking, you have location and aspects of are they indoors and outdoors, and aspects of what's their behavior, walking or sitting, and that sort of thing, and potentially who they're with and so on. And then you can start to get a pretty good guess that they might be outside smoking, particularly if they go out, stand there for a while, and then come back in the same route and don't really go anywhere outside. There's a chance they're just getting sun. Chances are they're seeing some. So here we're dealing with contexts where traditional data, we have many more participants than records per participant. Here we're dealing with quite the reverse often. Even if we have large numbers of people in our study, we're getting a lot more data per person than that way outbalances the number of people we have. So we might have thousands of people in a big study, but we have millions or tens of millions of records per person sometimes over the course of many months. And that requires different handling. This is from Xiaoyan, right? This is where people were spending time. This was actually her DFCI, and I think accounted for her project for this. But where they were spending time in Massachusetts, the areas they were spending time, the participants, and then she was looking at where they were reporting encountering tobacco messaging and whether there were certain areas, given the amount of time people spent there were areas that had disproportionate number of messages reported. And if you look at Ethica, and unfortunately this is too small for you to look at, but in a common study running a couple months, like this is our foodborne illness study that Iden helped run, here there were about 60 million records gathered for, I think, on the order of 40 participants over 3 months, 7.5 million GPS records, and orientation records, about close to 60 million, 91 million accelerometry records, etc. So we're talking about big volume. Big velocity. Well, we talked, this data comes in frequently. You think about Facebook updates or Twitter, app use, etc. Search behavior, to give you an example. Worldwide, this is, I think, a few years old now, but about 60,000 searches per second taking place through Google, I think. I think that's Google specifically. Sometimes this can be very insightful. So this is for whooping cough in Australia. Does anyone want to posit? Was there a time period here where something changed? Where would that be, roughly? That something changed. Turns out it's there. This was the tragic death of what was known in the media, the young child known in the media as Baby Riley. So Baby Riley was a baby who was just months old and who tragically died from whooping cough. And it was very publicized because whooping cough is a disease that's preventable with vaccines. But a growing number of people opt out of vaccines because they free ride on herd immunity, or they object, or they're skeptical, or they've never seen an outbreak, so why worry? And they're too busy for it. Baby Riley died, sadly. I mean, it's horrendous, and it really got caught up in the media, and people changed their behavior in terms of attitudes towards whooping cough. And you could see there's quite different patterns of searches after this. This is 2015, March 2015. This is September 11, 2016. This is 2013. You could see over the span of years, there's kind of a seasonal effect, and then there's a effect in terms of just sort of different, somewhat different patterns than before. Something happened. This, tragically, is for naloxone. Anyone know what naloxone is? Yeah, it's to treat opioid addiction, and particularly opioid overdoses. And these are searches from British Columbia for naloxone. How can I get naloxone? How can I administer it to someone who's a user? These are serious issues. Twitter, I mentioned Twitter volumes, or these days I think it's around 10,000 tweets per second. These are a little bit old. What's notable is that you can do geotagging and geoinferencing on Twitter data. So there's a certain fraction of it that's directly geotagged with lat long. There's other fractions where you can have the person's location or the tweet location mentioned by name, and you could figure it out. You also get retweet status, and you get liking status, etc. So worldwide, it's more than 300 million users, and as I mentioned, about half to one tweet per person per month for here in Canada, it seems. Variety. So I mentioned types of variety, and we can triangulate from many types of data that we're collecting for the same participant at the same time, and so on. So all of this points to a need for scalability. And we have very large amounts of data, but we have limited resources. CPU resources, memory, bandwidth of networks. And, there's a realization, particularly with the quantum limits Moore's law is run into. The opportunities for greater speed really come from intelligently, smartly using many computational resources together, coordinated faster, rather than speeding up our processors. We can no longer count on doubling the speed of our processors every 18 months, or the number of transistors on them every 18 months. Instead, what we can do is harness very large volumes of computational resources, cores, computers, in an effective fashion. Now, beyond the ability to just deal with the volume, working with big data raises other needs as well. One is to handle failure transparently across machines. I mean, if you're dealing with a whole farm of machines, machine failure turns from something that's an ad hoc, exceptional situation to a routine situation. When Google is running thousands of machines in a given facility, or tens of thousands, they can't treat a machine failure as something unusual happened. It has to be completely standard, time to change the machine, just like you might clean them periodically or what have you. You also have to deal with missing values. Data goes missing. Data is missing from some of the data sets. You have to be able to deal with that in your pipelines, in your processing of the data. To get you those results, you go through a set of stages. And you can't afford to have all sorts of ad hoc worries at earlier stages because there's missing data, and to deal with them in a very specialized way. You need a robust pipeline that will handle them. You need to handle error conditions, divide by zero, singular conditions. You've got such volumes of data that when you're processing it, it won't be unusual if something untoward happens. And critically, we need to be able to translate these needs from going from sort of scripting like interactive exploration of data, where we're interactively doing analysis to help us understand the structure of the data, what's there, spot patterns, and we have to go all the way up to rigorously tested, validated code bases that are production ready for ongoing insight, but can also handle these same problems: missing values, machine failures, error conditions. So these are the need for scalability. These are the need why we need to build software that can handle the large volumes of data. And I guess I should say the other thing here as well is that we're dealing with complex code bases that have complex multi-stages of processing. And we need software that's transparent and performant in handling these things. So next time, on Tuesday, we're going to be talking some about why Scala, like why we talk about Scala, talk about functional programming. Why does that play such a key role? And then talk about Spark, this platform we'll be riding on top of through the semester. Why does it play such a key role out there in industry when people are using big data, and why is it playing such a big role in our course for this issue of scalability? And we'll see how it enables things. We will then go on and discuss the first chapter, okay? Chapter 1 of the book. So I would ask you for next time to try to read the first chapter of the book, which will then orient us for the balance of the chapters that we'll be exploring. In the meantime, I will try to find the way that I found last year to access this through the libraries, okay? So that we can get the latest version here, okay? So thank you very much, folks. Thanks for dealing with the AV issues, and I will look forward to seeing you for the next class. Yes, Wade.
Just to clarify, which book you got, SFDS?
Oh, that's, sorry. Oh my gosh. It's FPIS. Thank you. I'll go correct that. This should be FPIS, and I'm referring to the first chapter of this guy here, functional programming, the red book. Okay, very good. Thanks very much for catching that, Wade. That's great. Okay, and I'll save this recording.